ఈ సెకండ్ యూనిట్లో లాస్ట్ టాపిక్ క్యాలిక్యులస్ రెసిడ్యూస్. సో ఈ రెసిడ్యూస్లో మనకి ఓన్లీ వన్ థీరం ఉంది. ఆ థీరం బేస్ చేసుకొని కొన్ని ప్రాబ్లమ్స్ ఉన్నాయి. ఇవి సేమ్ యాజ్ మనకి కాషీస్ ఇంటిగ్రల్ ప్రాబ్లమ్స్ లాగే ఉంటాయి. వెరీ వెరీ ఈజీ అండ్ వెరీ వెరీ ఇంపార్టెంట్. ఓకేనా? First definition is residue at a pole. So these pole definitions are two types. Number one is simple pole and second one is pole of order m. So first, the pole of order m is given function f of z equal in the form of sigma n equal 0 to infinity a n z minus a whole power n plus b1 by z minus a plus b2 by z minus a whole square and so on. So in this equation, b1, the coefficient of b1 is called residue of f of z at z equal to a. So this is the definition of pole of order m. Next theorem is Cauchy's residue theorem. So the statement of Cauchy's residue theorem is, let f of z be a single valued and analytic within and on a closed curve C, except at a finite number of points z1, z2, z3 and so on zn, and the residues r1, r2, r3 and so on rn are residues of f of z at these poles. Then the statement of Cauchy's residue theorem is integral over C f of z dz equal to 2 pi I multiple of the summation of residues, that is r1 plus r2 plus and so on rn. Proof of the theorem is, first to take the closed curve C and let C1, C2, C3 and so on Cn are, these are, we have to take the circles within the circle C and with the centers Z1, Z2, Z3 and so on Zn. They are lie entirely within the curve C, do not over the lap. So that means we have to take in the circle C1, C2 and so on Cn are, all circles are within the closed circle C. Now f of z is analytic within a closed curve C. So the function f of z is analytic function within the closed curve C. Then we have to using by Cauchy's integral theorem. So by using Cauchy's integral theorem for multi-connected region, we have integral over C f of z dz equal to, then in this closed curve C, we have take the circles C1, C2 and so on Cn. So we using multi-connected region, integral C f of z dz is equal to the additions of all circles C1, C2 and so on Cn. So that is equal to integral over C1 f of z dz plus integral C2 f of z dz plus and so on integral Cn f of z dz. So to say this is equation 1. By the definition of Cauchy's residue, R1 equal to 1 by 2 pi I integral over C1 f of z dz, which implies integral over C1 f of z dz equal to 2 pi I R1. Next, we have to take in the circle C2, then the residue, Cauchy's residue theorem, R2 equal to 1 by 2 pi I integral over C2 f of z dz. So, which implies integral over C2 f of z dz equal to 2 pi I R2. Similarly, so Rn is 1 by 2 pi I integral over Cn f of z dz, which implies integral Cn f of z dz equal to 2 pi I Rn. Substitute these values in equation 1. We get integral over C f of z dz equal to, first integration value is 2 pi I R1 plus 2 pi I R2 plus 2 pi I R3 and so on 2 pi I Rn. So that equal to 2 pi I multiple of R1 plus R2 plus R3 plus and so on Rn. So this is the Cauchy's residue theorem. Next, the formulas of simple pole and of order m. These formulas are used in the problems. The first formula is residue of f of z at a simple pole at z equal to a is limit z tends to a z minus a into f of z. So this is the formula for simple pole. Second one is residue of f of z at a pole z equal to a of order m is 1 by m minus 1 factorial limit z tends to a d power m minus 1 by dz power m minus 1. This is the differentiation of z minus a whole power m into f of z. So these two definitions are very important in this unit. First one is simple pole formula. Second one is of order m formula. Next problems are determine the poles of the function z by cos z and cot z. So the poles problems are important for 2 marks. So solution is to find the poles of z by cos z. So given function let f of z is z by cos z. To find the poles for the denominator value we have to take the equal to 0. So cos z equal to 0. So cos z equal to 0 means z equal to cos inverse 0. Cos inverse 0 means z is 2n plus 1 into pi by 2. That means for putting n equal to 0, 1, 2, 3 and so on. Next, the second one is cot z. So to find the poles of cot z, let f of z is cot z. So we have to find the poles. Let the denominator value is equal to 0. So in this problem, cot z, f of z is cot z. Then we have to write cot z is cos z by sin z. So let sin z equal to 0, z equal to sin inverse 0. So z equal to n pi. For putting n equal to 0, 1, 2, 3. So poles of this problem cot z is z equal to n pi. Next problem is find the poles of f of z equal to z square by z minus 1 into z minus 2 whole square and the residue of these poles. So solution is first to find the given function f of z of the poles. Next we have to find the residue of each pole. So given function f of z equal to z square by z minus 1 into z minus 2 whole square. For poles, let the denominator value is equal to 0. That means z minus 1 into z minus 2 whole square equal to 0. Therefore, we get z equal to 1 and z equal to 2. So, in these poles, z equal to 1 is a simple pole and z equal to 2 is a pole of order 2. Next, we have to find the residues of two poles z equal to 1 and z equal to 2. First, to find residue of f of z at z equal to 1. So, this is a simple pole. So, we have to know that simple pole formula is limit z tends to a z minus a f of z. That equal to here a is 1. So, limit z tends to 1 z minus 1 into f of z is z square by z minus 1 into z minus 2 whole square. After cancellation that equal to limit z tends to 1 z square by z minus 2 whole square. Then substitute z equal to 1, we get that equal to 1. Therefore residue of f of z at z equal to 1 is 1. Next, to find residue of f of z at z equal to 2. Z equal to 2 means of order 2. Already we note that the pole of order m is 1 by m minus 1 factorial into limit z tends to a d power m minus 1 by dz power m minus 1 of z minus a whole power m f of z. So this is the formula for pole of order m. Here m is 2 and a is 2. Then substitute these values in this formula. That equal to 1 by 2 minus 1 factorial limit z tends to 2 and d power 2 minus 1 by dz power 2 minus 1 z minus a whole square, that means z minus 2 whole square into f of z is z square by z minus 1 into z minus 2 whole square. After cancellation we get limit z tends to 2 d by dz of z square by z minus 1. So limit z tends to 2. This is in the form of u by v form. Then we have to differentiate with respect to z. Z minus 1 into z square is 2z minus z square into z minus 1 differentiation is 1 by v square, that is v square. So limit z tends to 2. So substitute z equal to 2, we get equal to 0. Residue of f of z after the 2 is 0. మ్యూట్లో పెట్టండి అమ్మా అక్కడ. Next problem is find the residue of z e power z by z minus 1 whole cube at its pole. First, to find the given function of the pole, let f of z is z e power z by z minus 1 whole cube. For finding the poles, let the denominator value z minus 1 whole cube equal to 0, z equal to 1. So z minus 1 whole cube means this is the of order 3. Then we have to find z equal to 1 is a pole of order 3. So in this problem, z equal to 1 is a pole of order 3. Next, we have to find residue of f of z at z equal to 1 of order 3. We know that the residue of f of z of order m formula is 1 by m minus 1 factorial limit z tends to a d power m by dz power m minus 1 multiple of z minus a whole power m into f of z. Here m is 3 and a is 1. So substitute these values in this formula. 1 by 3 minus 1 factorial into limit z tends to 1 d power 3 minus 1 by dz power 3 minus 1 multiple of z minus a whole cube into f of z is z e power z by z minus 1 whole cube. So after cancellation we get 1 by 2 factorial means 2 limit z tends to 1 d, d square by dz square of z e power z. So d square by dz square means 2 times differentiation of z e power z, that equal to 1 by 2 limit z tends to 1. So one time of differentiation of z e power z is e power z plus z into e power z. Next second time differentiation we get 1 by 2 limit z tends to 1 e power z plus z plus 1 into e power z. Then substitute z equal to 1, that equal to 1 by 2 into e power 1 into 3, that is 3e by 2. Next problem is find the residue of tangent at each pole. Let a given function f of z equal to tangent. For finding the poles, then we have to write tangent equal to sin z by cos z. For poles, let cos z equal to 0. So cos z equal to 0 means z equal to cos inverse 0. Then we get z equal to 2n plus 1 into pi by 2. So poles of tangent is 2n plus 1 into pi by 2 for putting n equal to 0, 1, 2, 3, 4 and so on. Next, to find residue of f of z at z equal to 2n plus 1 into pi by 2 for then substitute n equal to 0, 1, 2, 3 and so on. So poles are z equal to 2n plus 1 into pi by 2, put n equal to 0, 1, 2, 3 and so on. We get z equal to 5 by 2, 3 pi by 2, 5 pi by 2 and so on. So in general, let the pole is z equal to a. So we have to find the residue of f of z at z equal to a. So formula is limit z tends to a, z minus a into f of z. F of z means tan z. Tan z is sin z by cos z. So limit z tends to a, z minus a into sin z by cos z. Now we have to substitute z equal to a, that equal to 0 by 0 form. So then we have to using L hospital rule. L hospital rule means differentiating numerator and denominator, then substitute the limits. So limit z tends to a, numerator is z minus a sin z. So differentiation of z minus a into sin z is, this is the differentiation of uv, z minus a into cos z plus sin z into 1 by cos z differentiation is minus sin z. Now substitute the limits, we get sin a by minus sin a, that equal to minus 1. The next formula is residue of f of z. If f of z is of the form of phi of z by xi of z, then residue at a simple pole z equal to a is phi of a by z dash of a. So this is the also formula for simple pole. Next problem is find the poles and residues at each pole of 2z plus 1 by 1 minus z power 4. So in this problem, first we have to find poles and next we have to find residues of at each pole. So given problem is in the form of phi of z by xi of z. So in this problem we have to use simple pole formula is phi of a by z dash of a. So first to find the poles. For poles, let the denominator value is equal to 0. That means 1 minus z power 4 equal to 0. So 1 minus z power 4 we have to write, this is in the form of 1 plus a plus b into a minus b. So that is 1 plus z square into 1 minus z square equal to 0. 1 plus z square equal to 0. So z square equal to minus 1. That is minus 1 means I square. So z equal to plus or minus I. And 1 minus z square equal to 0. Z square is 1. Z equal to plus or minus 1. So poles are plus I, minus I, plus 1, minus 1. So 4 poles. These 4 poles are simple poles. Now in this problem we have to use the formula for simple pole is phi of a by z dash of a. First, phi of z is 2z plus 1 and xi of z is 1 minus z power 4. To find z dash of z is minus 1 is 0, z power 4 is 4z cube. So phi dash of z equal to minus 4z cube. Let first pole is z equal to 1. Therefore, residue of f of z at z equal to 1 is phi of 1 by z dash of 1. That is, then substitute a is 1, we get minus 3 by 4. Next, the pole z equal to minus 1. So therefore, residue of f of z at z equal to minus 1 is phi of minus 1 by z dash of minus 1. Then substitute a equal to minus 1, we get minus 1 by 4. Next pole at z equal to I. Residue of f of z at z equal to I is phi of I by z dash of I. Then substitute a equal to I. We get 2i plus 1 by minus 4i cube. Then multiple with I. That is numerator is 2i plus 1 into I. That means minus 2. 2i square. 2i square means minus 2 plus I by 4i square. That is minus 4. So residue of f of z at z equal to I is minus 2 plus I by minus 4. And finally at the pole z equal to minus I. Therefore residue of f of z at z equal to minus I is phi of minus I by z dash of minus I. Now substitute a equal to minus I. We get 2 plus I by 4. Next problem is evaluate closed integral C dz by z square plus 4 whole square, where the circle C is mod z minus I equal to 2. So solution is to evaluate closed integral C dz by z square plus 4 whole square. So in this problem, by using Cauchy's residue theorem, integral over C f of z dz equal to 2 pi I into r1 plus r2 plus and so on. So in this formula, first we have to find the residues. So how many residues to find in this problem. That means in this problem we have to find, first we have to find poles. So let f of z is 1 by z square plus 4 whole square. First to find the poles of f of z, then denominator value is equal to 0. First to find the poles, for poles let the denominator value z square plus 4 whole square equal to 0, z square plus 4 equal to 0, z square equal to 4 minus 4, that means 4i square, that is z equal to plus or minus 2i. So z equal to plus or minus 2i are poles of order 2. So in this problem we have to find the residues. For finding the residues, for given circle equation is mod z minus I equal to 2. So to write the circle equation in this value mod z minus I equal to 2, then substitute z is x plus iy minus I, then real part and imaginary parts. We have to using magnitude formula. We get circle equation is x square plus y minus 1 whole square equal to 4. So circle equation is x square plus y minus 1 whole square equal to 4. Poles are z equal to 2i and z equal to minus 2i. To verify these poles are inside or outside, first pole is z equal to 2i. Then z means x plus iy equal to 2i. Comparing real part x is 0 and imaginary part y is 2. So substitute these values in circle equation. We get 1 less than 4. So z equal to 2i lies inside the circle. Next, second pole is z equal to minus 2i. Z means x plus iy. So comparing real and imaginary parts, x is 0, y equal to minus 2. So substitute these values in circle equation. We get 9 greater than 4. So z equal to minus 2i pole is outside the circle. Next, to find the residue of f of z at z equal to 2i. Z equal to 2i is inside the circle. So to find its residues, that equal to z equal to 2i is a pole of order 2. Now we have to use the formula for of order 2 formula. At the pole z equal to 2i is 1 by 2 minus 1 factorial, limit z tends to 2i d by dz of z minus 2i whole square into f of z. F of z is 1 by z square plus 4 whole square. So in this formula here m equal to 2 and a is 2i. So that equal to limit z tends to 2i d by dz of z minus 2i whole square into then we have to write 1 by z square plus 4 whole square is equal to z plus 2i whole square into z minus 2i whole square. After cancellation of z minus 2i whole square, we get, so that equal to 1 by 1 factorial into limit z tends to 2i d by dz of z minus 2i whole square by 1 by z plus 2i whole square into z minus 2i whole square. After cancellation, limit z tends to 2i d by dz of 1 by z plus 2i whole square. So using differentiation formula, limit z tends to 2i minus 2 by z plus 2i whole cube. Then substitute z equal to 2i. We get 1 by 32i. So in this value, denominator value, we have we consist I, then multiple with I and dividing with I, we get minus I by 32. So this is the residue of f of z at z equal to 2i. So that equal to say R1. And second pole z equal to minus 2i is outside the circle. So integral over c dz by z square plus 4 whole square equal to, this is the formula for Cauchy's residue theorem, 2 pi I into R1 plus R2 plus R3 and so on. So in this problem, just we get residue R1. Residue R2 is 0. Therefore 2 pi I into R1. R1 is minus I by 32. That equal to pi by 16. Next problem is evaluate closed integral C z minus 3 by z square plus 2z plus 5 dz, where circle C is Number 1, mod z equal to 1. Number 2, mod z plus 1 minus I equal to 2. Number 3, mod z plus 1 plus I equal to 2. So solution is, to evaluate integral z minus 3 by z square plus 2z plus 5 dz, let f of z equal to z minus 3 by z square plus 2z plus 5. For finding poles, let the denominator value equal to 0. That is z square plus 2z plus 5 equal to 0. For finding poles, then this equation written as plus 5 means 1 plus 4. So z square plus 2z plus 1 plus 4 equal to 0. So z plus 1 whole square plus 4, then we have to write minus 4I square. So this is in the form of a square minus b square equal to 0. It can be written as a plus b into a minus b. So z plus 1 plus 2I into z plus 1 minus 2I. Here z equal to minus 1 minus 2I and z equal to minus 1 plus 2I. These are two poles for given f of z. So first given circle mod z equal to 1. To find circle equation, z means x plus iy. So magnitude formula x square plus y square equal to 1. To verify the two poles are inside the circle or outside the circle. So first pole is z equal to minus 1 minus 2y. Z means x plus iy. So comparing x and real and imaginary parts, x is minus 1, y equal to minus 2. Then substitute in circle equation x square plus y square equal to 1. That equal to 5 greater than 1. So z equal to minus 1 minus 2y pole is outside the circle. Next, to verify second pole. Second pole is z equal to minus 1 plus 2y. So z is x plus iy. Comparing real and imaginary, we get x equal to minus 1 and y equal to 2. Then substitute in circle equation, we get 5 greater than 1. So this is also lie outside the circle. So two poles are lie outside the circle mod z equal to 1. Then by using Cauchy's residue theorem, we get integral z minus 3 by z square plus 2z plus 5 dz equal to 0. So in this case, two poles are outside the circle. That's why the value is 0. Next, second circle is mod z plus 1 minus I equal to 2. Then we have to find circle equation. Then substitute z equal to x plus iy. Then real and imaginary parts. Using magnitude formula, we get circle equation is x plus 1 whole square plus y minus 1 whole square equal to 4. To verify two poles are inside or outside the circle. First pole is z equal to minus 1 minus 2y. So real part x is minus 1, y equal to minus 2. Substitute these values in circle equation x plus 1 whole square plus y minus 1 whole square equal to 4. We get 9 greater than 4. Next, second pole is z equal to minus 1 plus 2y. So x plus iy equal to minus 1 plus 2y. X is minus 1 real part, y real imaginary part is y equal to 2. Substitute in circle equation, we get 1 less than 4. So in these two poles, z equal to minus 1 minus 2y is outside the circle and z equal to minus 1 plus 2y is inside the circle. So first pole z equal to minus 1 minus 2i is outside the circle and second pole z equal to minus 1 plus 2i lies inside the circle. Now we have to find a residue at the pole inside the circle. So z equal to minus 1 plus 2i is inside the circle. Therefore residue R1 equal to limit z, this is the simple pole. So we have to using the formula for simple pole. R1 equal to limit z tends to a, z minus a into f of z. Now substitute f of z is z minus 3 by z square plus 2z plus 5. Now we have to write z square plus 2z plus 5 in the form of z minus of minus 1 minus 2y into z minus of minus 1 plus 2y. So after cancellation, in this pole z is minus 1 plus 2y. So R1 equal to limit z tends to minus 1 plus 2y, z minus of minus 1 plus 2y. Here a is minus 1 plus 2y into z minus 3 by z minus of minus 1 minus 2y into z minus of minus 1 plus 2y. After cancellation, then substitute z is minus 1 plus 2y. We get minus 1 plus 2y minus 3 by minus 1 plus 2y minus of minus 1 minus 2y. So R1 is 2y minus 4 by 4i. Then multiply with I and dividing with I, that equal to 1 plus 2i by 2. So this is the residue of f of z at a simple pole minus 1 plus 2y. That equal to, this is a value of R1. So next pole is outside the circle. So in this problem, we have to consider the only one residue of at the inside the pole. Z is minus 1 plus 2y. Second pole is outside the circle. So R2 is 0. Therefore, integral z minus 3 by z square plus 2z plus 5 dz equal to, by Cauchy's residue theorem, 2 pi I into R1 plus R2 and so on. So in this problem, R2 is 0. Then substitute R1 value is 1 plus 2i by 2. After cancellation, we get pi into 1 pi into I minus 2. Next, third circle is mod z plus 1 plus I equal to 2. So first we find circle equation. Now z means x plus iy. So taking real part and imaginary part, then we using the magnitude formula, we get x plus 1 whole square plus y plus 1 whole square equal to 4. So this is the circle equation. So circle equation is x plus 1 whole square plus y plus 1 whole square equal to 4. So poles are, first pole is z equal to minus 1 minus 2y. Here x is minus 1 and y is minus 2. Substitute these values in circle, we get 1 less than 4. Second pole is z equal to minus 1 plus 2y. X is minus 1, y equal to 2. And substitute in circle equation, we get 9 greater than 4. So z equal to minus 1 minus 2y pole is lies inside the circle, and z equal to minus 1 plus 2y pole is outside the circle. So to find residue of f of z at inside the pole, z equal to minus 1 minus 2y. So this is the simple pole. So R1 equal to limit z tends to minus 1 minus 2y into z minus a. A means minus 1 minus 2y into f of z is z minus 3 by z square plus 2z plus 5. Next to write z square plus 2z plus 5 is z minus of minus 1 minus, this is the factors of z square plus 2z plus 5. Z minus of minus 1 minus 2y into z minus of minus 1 plus 2y. So after cancellation, we get R1 is limit z tends to minus 1 minus 2y, z minus 3 by z minus of minus 1 plus 2y. So R1 equal to, then substitute z equal to minus 1 minus 2y. We get 2i plus 4 by 4i, that is I plus 2 by 2i. So multiple and dividing with I, we get 1 minus 2i by 2. Next R2. In this problem, R2 is 0. So z equal to minus 1 plus 2i is outside the circle. That's why R2 is 0. So integral over C, z minus 3 by z square plus 2z plus 5 dz equal to 2 pi I into only R1. R2 is 0. So 2 pi I into R1 is 1 minus 2i by 2. After cancellation, we get pi into I plus 2.